Okay, so as you're moving forward through your optics lab, eventually you're going to get to the point where they want you to build a telescope and build a microscope. And what is going on with a telescope and a microscope is instead of having just one lens, like a magnifying glass, you're actually going to use two lenses. You're going to use one lens to make an image, and then you're going to use that image as your object for the second lens. And so that's when you get what we call a virtual object. So this is kind of what it looks like. This is what a microscope looks like. Get the screen up here. So in a microscope you have the objective, which is the one you look through. So that's this smaller lens. No, sorry, the objective, which is the one that's next to your object. And then you have the bigger lens, which is the eyepiece, which is the one you look through. However, your object creates an image between the two lenses. This is the real image created by the objective lens. This real image can be used as a virtual object for the second lens. So the virtual object is on the opposite side of where you're looking through, and the image ends up being way outside of both of the lenses. So are you paying attention here? We got an object here. This is the real object. It creates an image here. You could use ray tracing, or you can use the lens equation to determine where this image is going to be right here. But this image is your object for this lens. It's inside the focal length of the eyepiece, so it creates an image on the other side. This is a virtual object because it's a real image, so it's a virtual object for the second lens. And then it creates another image out here, which is about 20 centimeters from your eyeball, and it's big so that you can see things and you can see detail. That's how a microscope works. Real object, real image. The real image is your virtual object, virtual image. So you make a virtual image with a virtual object, makes a virtual image way over here. And you can use the lens equation once here. Your object distance here will be positive. Your image distance here will be positive. But because this is a virtual object for the second lens, when you use the lens equation for the second lens, you're going to use a negative distance to your virtual object and then calculate the distance to your virtual image. Okay, so I'll do it one more time. Remember when we were doing lenses yesterday, and we did the lens equation, the distance to your object, to your real object, was always a positive distance, right? And when it's a real thing, like a physical thing, as your object that you're going to make an image of, that's always the case. Your object distance will always be positive in the equation. The equation looks like this: 1 over did they use D? Something like that. 1 over the distance to the object plus 1 over the distance to the image equals 1 over the focal length, right? That's your equation. Now, this is a positive number if it's a real object, if it's a real physical thing. So all we've ever used so far is a positive number for this. This one here is positive if it's a real image, in other words, an image you can project. But it's negative if it turns out negative, then it's what we call a virtual image, which is something that you have to look through the optic to see. And then the focal length is positive for focusing lens, and it's negative for a diverging lens.
And both of the lenses in a microscope are focusing, right?
No, not necessarily. You can have a combination of two different ones. In this case, they're both focusing, but they don't have to be. It just depends on how the microscope is built. So this is the case. Now, this, however, is something we didn't encounter. This one we always made positive because we've only had real objects. But you can use a real image as an object. In other words, you can make a real image with a real object, and then you can use this image to make a new image. And that's what they're doing here. But if you do that, that's called a virtual object then. And then it becomes the distance to your virtual object here becomes negative, and so you have to plug in a negative number there. virtual object distance, which means you're using an image for your object. So if you're using an image from one lens to make another image in another lens, then the distance to that now virtual object, which is the image from the first lens, is a negative distance. And that has to be plugged in that way. Now, the overall magnification of a configuration like this, where you have two focusing lenses in a microscope, is equal to the magnification of the objective and the magnification of the eyepiece multiplied together. So you're going to get one magnification from the first equation, another magnification from the second equation, multiply those together, and that's what you get. And remember, magnification can be measured, can be calculated by taking the distance to the image divided by the distance to the object with a negative sign in front. And that's how you get your magnification. Notice that the magnification for the first one is not very much, but the magnification from the second lens is huge, right? It's a big magnification from the eyepiece. And most really good microscopes actually have many, many lenses, not just two lenses in them. This is a very simple microscope. Most of them have much more than that, so that you get a very, very clear image. So let's see, in this case they actually do so here's the lens equation being used to calculate the distance to the image for the objective lens. And then if we calculate the distance to the image for the eyepiece lens, we'll notice here, distance to object, oh, they're actually just using this to, hold on a second. Actually, the way they've set it up, you don't have to have a negative distance for the distance to the virtual object. Let's see, is that right? Distance to object, focal length. Yeah, they're actually not even, they have it set up so they don't have to do that. So you don't have, this one can always just be positive, and then everything else will work out the way they've got it here. So that's fine. That works. I'm trying to figure out how they did that, but they're measuring from here to here. Okay. So don't worry about changing the sign of your distance to your object. That makes it much easier. Distance to object is always positive. Choose your focal length for converging or diverging lens, and then calculate the distance to the image. It will just come out. So just use this equation twice and you're good to go. That's what they do. Here they use the focal length of the first lens, which is the objective lens in this equation. So the first focal length is 6 millimeters, and then the distance to the object is 6.2 millimeters, and then they calculate the distance to the image. Simple. Then they do it again, but they use the distance as positive in 44 millimeters, distance to the new object, and then the eyepiece focal length is 50 millimeters. Calculate the distance to image, it gives you negative 367, which means the image and the object are on the same side of the eyepiece, right there. And you're good to go. So I was giving you too much information for what this book does. That's fine. I'm sorry?
What chapter are you in?
I'm in the next chapter. Because remember, the next chapter covers these compound lenses things, which your lab covers that as well. But it's the same stuff. We're not doing anything different here. We're just using the equation twice.
I'm just not sure if
You will eventually.
like 6 experiences.
But I just want you, when you get there, I don't want to have not covered it, so that you have some. And they'll cover it in the lab too. In the lab, they'll teach you how to do this. But I want you to have some experience with it, some knowledge of it before you get bombarded by it. So in the next part, they do a telescope, which is a similar thing. Telescopes can also be made with 2 focusing lenses, or 1 focusing lens and 1 defocusing lens, either way. But with a telescope, you're trying to you look at something that is infinitely far away, so all your light rays are coming in parallel. Something that is far away compared to the length of your telescope, all that light's coming in parallel, right? And so you can do your ray tracing this way and do the same thing. Or you can do the equations, but your distance to your object is going to be infinity. You're just going to use that as infinity, and 1 over infinity is, of course, 0. So it simplifies your equation. 1 over distance to image is just 1 over the focal length. So your image is going to be created at the focal length for the first lens. So stuff that's coming in from infinity will focus to the focal length of the objective, and then your eyepiece will refocus that image to a new position. So in this case, this one focuses the image here, and this lens focuses a new image over here. Okay? So in the equation, you just put in 1 over infinity for the eyepiece, for when you're doing the the objective equation. So if we do one down here, oh, and you can also do a mirror one, a mirror telescope. But it's the same equations, the same calculations. The only difference between telescopes and microscopes as far as any kind of calculation is when we calculate the magnification of a telescope, we don't calculate the linear magnification. We always calculate the angular magnification, which tells you how much angle has changed, how much angle you've magnified. And that's taken by taking the focal length of the objective over the focal length of the eyepiece, putting a negative sign in front. And that gives you your magnification for a telescope. So your angular magnification. So anyway, and like I said, they will cover these things. That's why I'm kind of going through it quickly. They will talk about these things, and they will step you through it in the lab so that you can learn how to make these calculations step by step. But I didn't want it to be the first time you saw it when you saw it in the lab. I just wanted you to have a little bit of background before you went into it. So I'm going to turn you loose on the labs, and we'll come back to this chapter next week on Tuesday, and we'll cover it in more detail, and then we'll put you back in the labs again. But then we'll also have a new homework for next week. Don't forget there is a homework this week, but it's not terribly difficult. It's mostly stuff that you've been doing in the labs, questions, conceptual questions, a few calculations, but not many. They're pretty simple compared. I mean, it just complements the lab. Scott's looking at this like, man, I hate this teacher. Now he's looking at me like he hates me. It's not as complicated as it seems when you actually do it in the lab. It'll all come together in the lab, I think. So I think that the labs teach it better than it can be taught in the book or in front of the class. This stuff is just a good hands-on thing. So go ahead and get started in your lab some more. And if you have questions, come and get me. Don't get stuck on things for too long. You guys are somewhere in the, you're doing lenses now, aren't you? Or are you still in mirrors?
We're now moving towards apparent depth.
So you're doing apparent depth in the prism?
Yeah.
Okay. Well,
We've done a
keep
little
moving.
bit of mirrors and a little bit of lenses.
Okay, well, keep going. The apparent depth, I think, is followed by total internal reflection. Is that right?
It's followed by reversibility.
Oh, okay.
We already did
Internal reflection?
yeah.
Okay.
Next we have dispersion, and then focal lengths and magnification of a thin lens.
Okay.
If we do that one, then we're
Okay. Well, just don't try to spend too much time on anything. If you get stuck for too long, always come and get me. And just try to go through as quickly as you can and learn things as quickly as you can. And then we'll get on to, by the end of next week, our goal is to be done with these labs that you've got and the eyeball lab that I'm going to give you. So we've got essentially this today, next Tuesday, Wednesday, and Thursday to get through these and one more.
I'm assuming we're going to have class on Wednesday then?
Yes, we will still have class on Wednesday even though there is inter-high day, because I'll just move you guys into the next room over and you guys will just work on labs all day Wednesday. Okay? Tuesday we'll come in and get going on this next chapter in some more detail, and then Wednesday we'll do labs all during class, and then Thursday we'll finish up. Any questions? All right. So Becca, do you want to hang